So you're not seeing the 3B radio wave characteristics?
T3B. Yep, I'm seeing the start page. Yes,
Okay,
and you've
there we
got a
go.
couple sidebars. There we go. Yeah, I see the full one now.
Okay, so now that we know all about radio waves, we'll kind of talk about how they propagate. In other words, get from point A to point B. When we talk about UHF and VHF signals, uh, they tend to be what we call line of sight.
Right.
So you have to be able to actually see the antenna that you're trying to get to, which means because of the curvature of the Earth, uh, you're going to be blocked at the horizon. So you can only make contact with somebody on the opposite side of the horizon that's basically the same height antenna as you. And there's a formula for doing that. Um,
Why you see some ginormous, like extremely excruciatingly high and painfully high radio towers, and some you don't.
yeah, the higher the antenna is, the farther you can go. If you look at that formula for the visual horizon, it's square root of the height in feet times this 1.23 number in miles. That tells you how far from the antenna to the horizon. So if you were had an antenna at 100 feet, then you could go 12.3 miles to the horizon.
Wow.
And somebody that had a 100-foot antenna on the other side of the horizon, you'd get you another 12, so you'd be about almost 25 miles. If you go, well, let's take, we have a repeater on top of the vertical assembly building out at the Space Center. It's like 530 feet. So it's got about close to a 40-mile radius. If you're in your handy-talkie and you're holding it up way above your head, say you got it up 9 feet, got a long arm, then it would be 3 times 1.23. So, a little less than 4 miles.
Gotcha.
Uh, in practice, it's going to be maybe 2 or 3 miles.
Wow.
Now, because there is some bending at the higher frequencies when they're close to the surface of the Earth, we have what we call the radio horizon, which actually lets the radio wave kind of bend and go a little bit over the horizon. So you can see that we changed the formula. So it's 1.414 times the square root of the height. So it gives you about an extra 15% in real life. And we call bending refraction.
Mm-hmm.
If you go to your ophthalmologist and they do a refraction test, that's what they're doing, is figuring out how much bending they need to do in the lenses.
Gotcha. All those flat earthers. Like, explain this one, guys.
Yeah, in flat Earth, you'd be able to go from
All the
one
way to
end to the
the
other,
other.
right?
Yeah.
Well, actually, it turns out uh, at the lower HF frequencies, we can actually bounce the signal all the way around the world.
Well, I know that my husband used to be able to listen to the Grand Ole Opry on Friday nights or Saturday nights um, in Gainesville, and they were transmitting from, of course, Nashville. but he could
Yeah.
listen. He could listen to them. And I remember one time the poor sergeant, he told them, please do not do this exercise this weekend. This is when we're having a solar flare to deal with, and we won't be able to communicate. Well, they decided to go ahead and do it anyway. And this is like pretty much not at the start, but more people had like handheld, the smaller phones. We couldn't even talk 3 miles away. Our signals were like toast. But we could hear people in Korea and Australia, but we couldn't even talk 3 miles away. It was incredible. They say on the 30th of October is supposed to be a huge one. It's supposed to disrupt all kinds of stuff.
Yeah, we'll talk about those a little bit more. So, any questions on the visual or radio horizon?
No, it makes a lot of sense.
Okay. Here's just a diagram showing,
okay,
what that distance is in miles based on the height.
Mm-hmm.
So, when you're talking point to point, you get to add the two together. And obviously, like if H1 over here was way down here with a much taller antenna, you could still talk to them.
Yeah.
So why is the radio horizon for VHF and UHF signals more distant than the visual horizon?
Charlie.
Charlie. Why are simplex UHF signals rarely heard beyond the radio horizon? And simplex means that you're going point to point, not through a repeater.
Say Charlie.
Okay, so we talk about different propagation modes, and one of the things that happens, you can have what we call multipath. You used to be able to see it when you were watching broadcast TV over the air, and sometimes you could get the signal over two different paths and get, like a ghost. You have the same kind of thing with radio waves, where they can bounce off of different things and have different path lengths so they don't arrive at the same time. And that can cause them to be in phase or out of phase, so they can either reinforce the signal or cancel the signal. And if you're moving, you can get real fluctuations. And also, just by moving a few feet, you can get to a point where you don't have the multipath. If you're mobile in a car, you can get what sounds like, we call it picket fencing, and you hear the signal come and go, like somebody, riding on a bike and with a stick on the picket fence.
Yeah.
If you're doing digital communications like digital voice or some of the other digital modes, they don't really work well with that kind of a signal. Wherein
we call them bubbles.
In analog mode, you kind of hear the fluctuations. It gets louder and softer. With the digital, it's kind of either there or it isn't.
Right.
So you can get errors with multipath in digital modes, particularly mobile. This is just a picture showing you've got a transmitter up there on top of that building, and you're getting reflections off all these other buildings, all coming back to this car at the same time. That would be a lot of multipath. And as that car moves, those paths are all going to change.
Mm-hmm.
So why do VHF signal strengths sometimes vary greatly when the antenna is moved only a few feet?
Charlie.
Charlie, what's the meaning of the term picket fencing?
Bravo.
What effect does multipath propagation have on data transmissions?
I would say delta.
Very good. Okay. So we talked about line of sight. Now we'll talk about repeaters. With the repeater, what you're doing is you're talking to a transmitter and receiver that receives on one frequency and transmits on a different frequency. So it basically is a relay.
Okay.
And normally you put a repeater, at least a repeater antenna, up as high as you can to get the widest distance. And it allows you to get over buildings and obstructions and things, get much farther. Out where they have mountains, a lot of times they'll have repeaters up on top of a mountain, so you can talk to people on the other side of the mountain.
No bear went over the mountain. No, this is like the cell phones that they have the towers every few miles.
Right. Those are repeaters for cell phones.
Mm-hmm.
Um,
Avoid trees.
You have what's called an indirect path, where you're actually using the fact that you're bouncing the signal off of some building or something to get to your destination, as opposed to a direct line of sight. There's also a thing called knife edge diffraction, which you see in visible light, but it also has a similar effect on radio waves, where a kind of a sharp edge, like the edge of a building or the peak of a mountain, will actually cause that wave to bend. It kind of more diffracts it, but it still bends it. So you can go around buildings or over mountain peaks to some extent.
Do you have
there's
to,
also
is that like where you have to like find a signal, or it just ends up happening?
Well, it just happens, but you can take advantage of it if you are in the right spot and know what you're doing.
Gotcha.
There's also absorption. UHF and higher signals tend to be absorbed by water. So anything with a lot of water, heavy vegetation, rain, snow, people, trees, absorb very high frequency signals. I don't know if you've ever been to any of the big expositions or things, where there's tons of people in a big room and everybody's trying to use their cell phone.
Yeah, at the football games, you can't get a signal.
It's because one of the reasons is because of all the people absorbing the signal.
Yeah, it happens at happened at the Gator game, and we're up in the upper section where we should be getting more signal than people down below, but we're all doing this, putting the phones up in the air looking for a signal.
Yeah, I don't think most people realize that humans are mostly water.
Yeah. What, 96%?
That's something like that.
92 or 96, I forget. It's up there.
Okay, there's just showing, where you're going over the mountain.
Yep.
So when using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight?
Bravo.
Now, in that question, to me, the directional antenna doesn't really make much difference.
Okay, if it's not Bravo, I don't know. I don't understand. To communicate with distant repeaters.
Bravo.
Okay.
I think they put directional antenna in there so that Charlie would be wrong.
Okay. Yeah.
Because if you had an omnidirectional antenna, you could actually get the signal on the long path, which is the opposite direction. In other words, it would go all the way around the world. Although, when we're talking about VHF, UHF, that's not going to happen anyway. This is one showing knife edge diffraction over a mountain peak.
Well, that's pretty
where
cool.
the signal actually gets diffracted down. So if you're down in this lower region, you can pick up the signal. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
Alpha.
That's a hard one, wasn't it?
Yeah, all the other choices.
What's the effect of vegetation on VHF and microwave?
Bravo.
Okay, I mentioned polarization earlier. So it really is the orientation of the electric field with respect to ground. So if you have an antenna like in the animation, which would just be a simple dipole, it's oriented horizontally, and you can see that the green, which is the electric field, is oscillating horizontally. And so we call that horizontal polarization. If I was to rotate that antenna 90 degrees so it would be vertical, then it would be vertical polarization because the field would be oscillating up and down. Does that make sense?
Yeah. Horizontal to horizontal and vertical to vertical.
Pretty much. So, where this comes into play, if we're doing a line of sight, typically with VHF or UHF, we need to have the same polarization. In other words, if you're using a vertical antenna, the person you're trying to contact needs to have a vertical antenna.
That makes sense, yeah.
Are you familiar with polarized lenses and sunglasses?
Yeah, they can cancel each other out when you turn them just right.
Right. Same effect. So if I had a vertical and a horizontal, I'm going to reduce the signal by probably 1,000.
Yeah.
If I'm trying to do any kind of long distance with VHF or UHF, where I'm doing single sideband or CW, typically you're going to use horizontal. It's easier to implement antenna-wise, and that's what most people would be using. So you'd be going horizontal to horizontal. If you're doing like a handheld, a walkie-talkie, it's going to be vertical unless you turn it sideways. So all repeaters I'm aware of are using vertical antennas because it's omnidirectional.
Yeah, you talk about like what I see on the towers, how they're upright.
Well, Yeah. What you see on a lot of the towers are uh,
They're like the rectangular things. Antennas.
the the repeater antennas aren't really very big, so they're not that easy to see,
Okay.
especially if they're up high. Because remember, wavelengths are shorter at high frequencies.
Yeah.
So if it's a quarter wave antenna, it's not very big. This is showing standard, what we call linear polarization, where the green is the E field,
Mm-hmm.
and it's horizontally polarized. The one below it is showing what we call circularly polarized, where the E field is actually rotating. And we'll talk about that a bit more. This is an example showing polarization as you cross the polarizing filters, and you get almost nothing out. So what property of a radio wave defines its polarization?
Alpha, orientation electric field.
All right. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization?
Well, Bravo for sure. Because we didn't talk about Echo.
What antenna polarization normally used for long distance CW and single sideband contacts on VHF and UHF?
Charlie.
So we learned the formula for line of sight and the radio horizon. One's visual, one's radio horizon, so you get longer distance. We talked about multi-phase, where you get things in and out of phase. You can have picket fencing. You get high error rates on digital data transmissions. You can make use of reflections off of buildings to make a connection, or knife edge diffraction, where will actually bend around a sharp edge. I never considered a mountaintop a sharp edge, but apparently it is. That water in just about any form will absorb high frequencies, UHF and above. Polarization is the orientation of the electric field relative to the Earth. We use horizontal for long distance communications and vertical for line of sight. All right, where'd my thing go? I keep losing my control.
Maybe it's something with the Zoom people.
I guess I have to stop the share.